All right. So again, the office hours will be just in a Zoom meeting. And then I have a separate Zoom meeting for office hours before class and on Tuesdays. If you need to set up special office hours, let me know. It's much easier now for me to set up one-off office hours because I don't have to drive into campus. So it doesn't matter what day it is. Okay, so just feel free to email me or contact me on Piazza. Does anyone have any particular logistics questions other than what I just covered? No? All right, then let's go ahead and get going with InStepTD. I'll finish up early with InStepTD. So, right, InStepTD, we basically had right, something like this, right, where we're taking not just a single step, but actually multiple steps and looking at a sequence of rewards, discounting them appropriately. When we're doing, so that worked great for on policy, but if we're doing off policy, right, we have some behavior policy B, and we have our target policy pi, then we need to do some sort of weighting, right, adjust it to adjust for the fact that the behavior policy may be taking some very common action as far as the behavior policy is concerned, but some very uncommon action as far as the target policy is concerned. So we have our rho sub t, where rho sub t equals the probability of taking action t given state t divided by b of action t divided by state t, right? So this is just review, but it has been about 2.5 weeks, so it's worth reviewing. And this is the state value that we're using, okay? The state value is important. So we're actually taking the rho sub t and multiplying that by all of our total discounted reward. So both our immediate reward and our discounted reward. What we can do here is make an adjustment to decrease the variance. So what happens if, and by the way, I forgot to mention, I still will call on people. So I'll just call on, let's see, let me see the order in which to do this. It doesn't show me people alphabetically, but we'll try alphabetical. So Ali, you're gonna be next, just to warn you. So the question is, given this formulation here without the control variant, what is the reward if we have a 0 rho sub t? That is, the behavior policy takes some action that the target policy never would. And actually, yeah, go ahead, I'm using.
Oh. Wait.
Yeah.
Oh, wait, hold on. I accidentally scheduled a meeting. Hold on one second. Okay, we're good. Sorry, could you repeat the question one more time?
Yeah, so the question is, if rho sub t is 0, that is, if our target policy, our pi is 0 for some behavior, for some action that the behavior actually took, what's our target reward going to be?
0.
That's going to be 0, right? So if we have a state value with a particular state value, and then we hit this particular action, then that's going to tend to push the new state value towards 0, right? So we've got this current state value, which is, I don't know, let's just make it x. And we've got our target state value of 0. So we're now going to move some percentage of the way from x to 0, depending on our setting of alpha. Right? Well, that seems kind of, what I call it, well, extreme, I guess, to say it's 0. Because another thing we might say is, well, if we don't know what it is, let's just use our current estimation of it, right? Our current estimation is, our current value function for that state. If we say that we're going to use our current value function for the state, if rho is 0, right? So basically, if rho is 0, then we're going to have 0 times that plus 1 times our current value. Okay, so that what'll happen is we just won't change it, right? So if we get a rho of 0, it says don't change the value for that state. Okay, as opposed to changing the value to try and become 0. Does the difference make sense? So see why we would have less variance in that second case. So this is the control variant. So this part of it is called the control variant. Okay. Now, is not kosher to just add whatever we want to this function, right? We can't just add anything we want here. We need to add something such that we're not changing the expected value. Okay. And the expected value of 1 minus rho sub t times, well, what's that equal? Well, we do know one thing. We know that the expected value of rho sub t equals 1. Okay, that was shown, I think it was an exercise maybe, a chapter or two back, which kind of makes sense if you kind of think about the fact that if, let's say, rho is very large, that means we have a large pi and a small b. Somewhere else, there must be a large b to account for that. Okay, so since the expected value of rho sub t is 1, then, and since rho sub t is independent of vh minus 1, then we can actually separate these out, multiply the two expectations by themselves. And the first expectation is going to be the expectation of 1 minus rho sub t, and that'll be 0. So our total expectation is going to be 0. Okay? So that's why it's fair to go ahead and add this control variant, because of the fact that the expected value is going to be 0. So it's not going to adjust the bias at all. It's just going to change the variance, reduce the variance. Questions on that topic? Okay. Oh, one other thing. Of course, I'm going to post this video. You may have already seen that these slides were posted. I'm going to also then post the slides after I edit them and write them. So those will be available shortly after lecture today. All right. So that's the important sampling when we're doing the state value. When we look at the action value, things are different. Okay. When we look at the action value, it's different because of the fact that when we're looking at Q of S sub t comma A sub t, we're not supposed to take into account what the probability is of taking action A sub t, right? We're supposed to take action A sub t, and then from then on, follow whatever our policy pi is in subsequent actions. So because of that, our reward here doesn't have a rho factor, right? We don't use rho sub t. We don't care about rho sub t, because rho sub t tells us the ratio, basically, of, right, pi of at given st over b of at given st. And we don't care what pi of at given st is. Could be 0, could be 1, could be, we don't care, because we don't, that doesn't affect our evaluation of what the reward is. We do care about the reward for any future actions. And that's where we got the rho sub t minus 1 there. We can do the same thing as far as adding an action variant. As adding a control variant. So we're going to add a control variant to this to try and reduce the variance. The key on adding a control variant is, again, we need to make sure that the expected value of the control variant equals 0. Okay. So here's our control variant. Our control variant is this here. Okay. And we're going to actually take an expectation of that. So we're going to take the expectation of the expectation minus rho t plus 1q. Okay. So let's pull that apart a second. If we look at the expectation, and because of the linearity of expectations, we can break apart the difference here. But let's look at this part. So the expectation, according to policy B, of rho sub t plus 1 q what's that equal? Well, remember the reason we went ahead and defined this rho was that so we could go ahead and have an unbiased estimate, right? We were taking estimates from sampling from B, and we wanted to convert that to estimates from pi. And so what we had said was if we use this importance sampling ratio, that we could then adjust to from a different distribution. So we're moving from the distribution according to B to the distribution according to pi. Does that one make sense? Any questions on that? You remember doing that? Okay. Well, this is our basically just our value function, right? That says if you're sampling from our target policy, the Q values, that's really just a V value, right? We're going to actually define V hat to be this summation over all our actions of that. Okay, so it's basically just summing up, doing a weighted sum of our Q's is going to give us our V hat. So this equals, let's see, so we have expectation of B converts to expectation of pi, which converts to this VH minus 1. And now, pardon me as I get used to this. So now what we can say is what's the expectation of VH minus 1 of ST plus 1. And let's see, Ali, you were first. Bowen, I think you're next alphabetically, and the rest of you can kind of keep track of where you are alphabetically and we'll be coming up. So Bowen, what's the expectation of VH minus 1 of ST plus 1? And you can unmute yourself, or let me try unmuting you. Your mic is not working. Got it. So we will answer the question, let's say, in the chat. How about? So our question again is, we've got this V, this state value function, and what is our expectation of it? So we have a state value function VH minus 1 of ST plus 1, and now what's the expectation of that? And just as a hint, what's the expectation of 5? In fact, you could just start with that. So the expectation, yeah, that's just the constant 5. Well, our value function is something similar here, right? We have, it is itself an expectation. So we're now just down to a constant. So that this is just VH minus 1 of ST plus 1. Yep, exactly. So this guy just turns into this guy, okay? And the rest of it stays alone. We haven't actually even shown why is this expectation equal to 0. The reason the expectation is equal to 0 is that we have got, let's see, we have got the expectation of this guy, rho t plus 1 times q, minus rho t plus 1 times q. Okay? If we take an expectation of a value, some random variable, right? So we have some, whoops, we have some expectation of r and subtract it from r. What's the expected value of that? Let's see, Daniel A. So for any random variable, what is the expectation of r minus r?
I think it's just 0.
Yeah, it's going to be 0 because this is going to be the expectation of r minus expectation of r, right? Basically, if you take the average, let's take the mean of a whole distribution and subtract it from a sample from that distribution. And you look at then the expectation overall, that's going to be 0. Right? So this is showing us that our control variate does correctly have the property that its expected value is 0. All right, so and all we have done on the last line is just basically rearrange some of the terms. Okay. So if we look at this case and see what happens if rho t plus 1 equals 0, then we lose this term. And we're going to basically just say we are the reward, the immediate reward, plus our discounted estimation of the next state, which is going to be the weighted sum across all the Qs for all the actions weighted by pi. Okay. And so that is going to, again, have less variance than if we just used this first equation without the control variate, where this whole term would go to 0, and we just end up with the immediate reward and assume we had no future reward. Here, our future reward we're going to assume is whatever our current estimations of Q. Okay. Let's say you wanted to, let's say, for example, you were using a behavior policy whose characteristics you did not know. So you didn't know the probabilities. Could you use that important sampling, Daniel Y? Okay, so the question is, and let me write it again, if black, if we don't know B, can we do importance sampling?
I mean, it seems like your at least our previous formulation, it depends on the ratio of pi to b, but apparently you probably can do it because that's the point of this slide.
Well, actually, this slide is without importance sampling. So my question is not, so my question isn't, can we do it at all? It's, can we do it with importance sampling?
Yeah, with importance sampling, it will be impossible.
Yeah. So the answer is no. Requires rho, which requires B. So what are some circumstances in which we don't have B? We've got some policy going and we're not exactly sure what it is. You know, we just look over there and see that there's some agent that's taking some actions. We have no idea how it's deciding to take those actions, but we can see the rewards that are coming out and we can see the states that it's going to. Can we learn from that? And the answer is yes, we can learn from that. And we're going to look at that in terms of tree backing. Okay, so does the rationale for this make sense? Right? The rationale is we are sampling, or we're doing a sample, we don't know what the distribution is. So therefore we can't correct for it to our pi. So here's what we're going to do. Let's look at...
Professor, I think Shannon has a question. She said in the chat she had a question.
Shannon, go ahead.
I did. It wasn't that important, so I didn't bring it up when you kept moving. But like,
okay.
I'm wondering if you could redefine or like re-explain what V bar was.
Yeah, so V bar
is distinct from like B.
There's no room here. Let's see. So let me just define V bar, right? V bar is going to be the summation for actions of pi of A given S times Q of SA. So a lot of times we may be estimating V without having any associated Q, right? So we've certainly done that in the past where we're estimating state values. In this case, we're estimating, so we are estimating action values. Q of S comma A, and those determine a value for the state, right? We're just separating V hat as opposed, sorry, V bar as opposed to V because we're not directly trying to estimate the value function or update the estimate. Does that answer the question?
Yeah, thank you.
Okay, great. Okay, so let's look at first just expected SARSA, right? This is our backup diagram. We have one step. We go ahead and take an action. We get a reward, and then we do a weighted sum, right, of our Qs. So there's nothing new about that in particular. So this is one step SARSA. Sorry, one step expected SARSA. And we can use expected SARSA, this one step expected SARSA off policy, right? So because whenever we take, we don't care what action we actually took, because we're going to just look at the weighted sum over all the actions we could have taken. Right? So what the important information we're getting from our environment is we're in a state, from our previous state, we took an action and then got ourselves into a reward and a new state. Right, here's our S prime. This is our A and S. And from there, then, we don't actually try and take an action in order to update Q of AS. We just look at all the possible things we could have done. The end step expected SARSA right, we take basically take n minus 1 steps, and then the last step, we go ahead and do expectation. Okay? So for all of the previous steps, if we are off policy, we would have to be taking into account importance sampling. So we would have to take into account basically importance sampling, you know, a row here, a row, what? Row 1, a sorry, let me get rid of the row 1. A row 2, you know, a row 3, all the way down to here, a row n minus 1. And then unlike in-step SARSA, in the in-step expected SARSA, our very last step, we won't use importance sampling. We'll just use our expectation, our weighted average. Okay. So this still doesn't work, right? It still requires us to do importance sampling as long as n is greater than 1, right? As long as we're doing n step, not 1 step. So in this 1-step case, our definition for our total reward is really just our reward plus our discounted weighted sum. Yeah, so this corresponds to this case. And then I'm going to look at a 2-step in a moment. So let's look at the 2-step. Right, the 2-step is this one where we go here. We have our state, we take an action. We have another state. However, what we're going to do is do a weighted sum at the first state too. So at that first step. So we're going to say, we're going to take RT plus 1. So let's just find where RT plus 1 is here. RT plus 1 is we take a, so this is S comma A. This is really S of T, A sub B, right? That's where we're starting. We go ahead and get our reward of RT plus 1. This is ST plus 1. This is AT plus 2. This is AT plus 1. Let me make this so I can read it. This is ST plus 2, and here we have RT plus 2. Okay. So what we're going to do is take RT plus 1, right? So this is our immediate reward. And then, of course, we do our discounting. And now we're going to take our weighted sum at the first level. So our weighted sum is going to be this guy plus this guy, everyone not equal to the action we actually took. Okay, so it's all the other possible actions and their probabilities according to our target policy, right? according to pi. So these are, we're looking at the actions not taken and look then at our estimates of our rewards from those actions. Does it make sense so far? And then what do? Then we go ahead and discount again. We're going to take the probability of having taken the actual action. So that's this probability here. We're going to take the second reward, which is this here, and then go ahead and, what colors can I use now? Kind of out of colors. I guess I'll use red. So those would be these. Okay. So what we've got is this tree, and all the leaves in the trees are Q values. Okay, so we have let's just circle the leaves, or I'll square the leaves, right? These are the leaves. So we have all these different Q values. Q for this, 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 right? We know the state of this Q is this state, and we know the action of this Q is this action here. We know the state of this Q is the state over here, and its action is this action. Okay, so we know what Q values to get, and then the question is, how much do we weight them? Well, we weight them by the probability of actually getting to any one of those leaves. So the probability of, along with, we need to do a discount factor as well. So depending on what level it's at, we're going to have a discount factor associated with it. And then we're also going to have the probability of getting there. So if we look at the probability of this guy, the probability is just here, the probability of having taken that branch. So this is the probability of taking, let's call this one A1. We can't call it A sub 1. We'll just call it A, some lowercase a. So it's the probability of A given S sub T plus 1. Okay, assuming that's S sub T plus 1. So it's the probability of having taken this branch. That's what we multiply this leftmost, topmost node by. Similarly, if we look at the right node here, we're going to multiply it by a different probability, the probability of having taken this particular action. Okay. It's when we get down to the second level that it's more interesting, because we have not only the probability here to multiply, but also the probability here to multiply. So what's the probability that we took the action that took us to this state, and then the probability from that state that we went on to this leaf. Okay. So that is captured. If we notice, let's give very hard to come up with enough colors to show things. But basically, we have this pi times this pi. So the pi of AT plus 1 given ST plus 1 times the pi of A given ST plus 2. So this is the two-step. The n step just generalizes directly from there. The n step just says, we look at the immediate reward here. We then discount. We then branch out and look at our expectation for everything except the action we're actually taking. Okay? Why are we taking this action? We don't know, right? We're off policy. We just observe that this action is happening. And we say, okay, for every other action from this state, what's the probability of having taken it? And what is our estimate of the reward from doing that? And then we say, okay, for the action that was taken, this AT plus 1, what's the probability that we did take it? And then go ahead and recursively calculate from there. So what we end up with is a tree where we have a bunch of actions that were not taken. And we use the probability that we do know because it's assumed we know pi, right? But we don't have to know B. We don't have to know why it is that we are going from state to state to state here. That is, more accurately, we don't have to know why it is that the actions are being chosen. So why did we choose to take this action and not another action? I don't know. We just did. Why did we choose to take this second action? We don't know. So it's not dependent on our behavior policy. And yet, we can still come up with an estimate of our total reward for having started in this state, taken this action, and then following our policy. Okay. So I'm sure there must be some questions, so go ahead.
So would you use an epsilon greedy policy or like a purely greedy policy for pi?
For pi, so it depends what we're trying to do. Are we trying to estimate pi or are we trying to improve it? Right? Is this a control? And that's the question. So if we were trying to just estimate it, then we would use pi as is and not change it. If we were trying to improve it, then we'd probably use a greedy policy. As to our off policy, our behavior policy, what are we going to use there? We just need to do something that does exploring. Okay, all that was really required for us to end up converging to good Q values is that we do sort of eventually explore everything infinitely many times. Other question?
Hi, can you hear me?
Yeah, who's talking?
Sean.
Sean, there you go.
So when in practice, when you're generating these trees, are you starting at a starting point and then generating or making end decisions or end actions? Or are you generating a full episode until your terminal state and then you're looking at the final end steps?
You're probably going to be doing it similar to how we had done our in-step algorithms that we looked at before, in that you are going to start at whatever your start state is, take an action, and then you're going to keep going until you've done n actions, and then you can kind of go back and compute your whole tree of all the states that you've gone to, and then go ahead and update the first state action pair, the Q value. And then once you have sort of these n, you can take one more action and then update the next one, which is looking in back. Does that explain that? Or yeah, does that answer your question, Sean?
Thank you.
So unlike, right, we don't want to wait till our episode is finished. because we might not ever finish. So we don't want to require, as Monte Carlo does, that we finish an episode. Okay.
I have one question. How does this affect bias and the variance that we were discussing before with the different sorts of ordinary and weighted importance sampling?
Yeah, so what happens is when we are doing sampling, that is, we're doing the importance sampling ratio. So we're basically taking just a sample through the behavior policy and then weighting it for the target policy. We're going to have higher variance than the tree backup. So the tree backup is going to basically have lower variance than doing the importance sampling. So let me just actually write that one down. So the tree backup and the importance sampling. And if we look now at, just move that, that's handy, bias and the variance. So this will be lower and the variance is going to be higher, but the bias of the importance sampling is going to be lower and the tree backup bias is going to be higher. Okay. The bias will go down over time. But to begin with, we're going to find that the importance sampling is going to give us lower bias, which brings up the question of what if we could somehow combine the two? Okay, maybe use importance sampling early on and then use tree backup later, for example. Does that answer your question, Lamaz?
Yes. Could you explain a little bit why the bias goes down over time with the tree backup?
So let's see if I can give you that. I can't right now. I'll make a note on that and see if I can address that on Wednesday. 1 second. Other questions? Okay. So Q sigma is this combo approach that basically says we could go ahead and combine, or not even going to say combine, interpolate between tree backup and this per decision importance sampling. Okay, so we can smoothly move from one to the other and actually also over time change how we do this. So let's just look at our tree backup and our per decision importance sampling and look at how similar these equations are and then how easy it is to do a weighted mean between them. So let's first actually look at the per decision importance sampling. This is just a rewrite of what we'd seen before, basically, where our rho sub t plus 1 here is multiplied by our subsequent return minus our Q value for the action we actually take. And then we add on this term for the value function of the state. The tree backup return, we started with this first line that is basically just a restatement of what we had. So the immediate return plus discounted weighted sum of all the actions we didn't take, plus then a discounted probability that we did take the action that actually happened times then the sum from that point. Well, we can rewrite this as, so we can rewrite this, let's see, this piece here as the V bar, right, which is just this summation of all actions, and then take out the action that we actually did choose, right? So we have a summation, A not equals AT plus 1 of some value. And that's the same thing as a summation over all A of the value minus the value at A. Okay. I'm butchering notation here, but I hope it makes sense. So this summation of all A of our Q value is just equal to V bar of our state. And this is minus Q of S and the actual action that was taken. And then we just move these around a little bit, right? So we've basically got this guy moved into here, and we've pulled out this guy over here. But what we can see is that these two definitions of the return are fairly similar. They both start with an RT plus 1. Okay, let me. So we've got an RT plus 1 here and an RT plus 1 here. They both end with a gamma VH minus 1 ST plus 1. They both have GT plus 1H minus QH minus 1 here. So the only parts that are different, and they even actually have a gamma here. So the only parts that are different are this guy and this guy. Okay, one is using rho and one is using pi. Clearly the one that's using rho is the one that's doing importance sampling because it's the one that has to know what the probabilities of the behavior policy are. So what we can do is just combine them and use a weighted sample, so, or a weighted mean. So we're going to use this weighted mean here. And what we're using is sigma as our weight. So sigma is going to be, it's going to be in the range 0 to 1, right? So it tells us what fraction of rho to take. Okay, sigma basically tells us what fraction of sampling to do. So how much of the rho should we use? And then conversely, the 1 minus sigma t plus 1 tells us how much of the pi should use. So the fact that sigma is within the range 0 to 1 smoothly, continuously, allows us to get that smooth transition from importance sampling to tree backup. Okay, and at a particular level. So sigma t, the sigma i's, let's say, can be different. So we can change our sigmas over time We could also change them. Let me give you a good example. Let's say we have a behavior policy where sometimes we know the probabilities of the action it takes, and sometimes we don't. In that case, for the times that we do know what the behavior policy probabilities are, we have a row, and therefore we can take sigma to be something that is 1 perhaps, or close to 1. On the other hand, when there are cases where we don't know what the sigma is, then we'll go ahead and rely on the tree backup. Why don't we use tree backup all the time? It's really this, there's a couple of reasons we don't use tree backup all the time. Can anyone, opening up to anyone, can anyone give me a reason why the tree backup would be expensive or difficult to compute? Just unmute yourself and answer, whoever.
You may have a lot of actions that you have to sum over.
Yeah, that's our killer, is we may have a lot of actions that we have to sum over. This is Nick's, right?
Yeah.
Yeah, so if you've got an action space with, I don't know, 10,000, 100,000 actions, then it may be prohibitive to make that calculation. And there's really a trade-off. So let's even make this simpler. Let's just look at SARSA versus expected SARSA. Okay, why would we not always want to just use expected SARSA? Because it may be so expensive because you have all those actions, and you may be trading off doing one of these calculations and updating a Q value. Whereas if you hadn't spent all your time in computation, you could have gotten more samples. So you could have instead gone ahead and experienced in the environment more things, updated your Qs by the time you've managed to update 1 Q in the expected case. So the same thing could be true here in the tree backup. If it's expensive to calculate normally because you have a lot of actions, then that's not so great. One paper, let's see, I don't think it's referenced in our, not sure whether it's referenced in our book or not, but let me see. So for one paper, they basically looked at what works best in terms of this sigma value. So they looked at, sigma equals 0, sigma equals 1, sigma equals some constants like 0.2 or 0.6 or so on. And what they found was intermediate sigmas worked better. What worked even better was I don't remember what they call it. I call it something like a descending sigma. So start sigma at 1 and then reduce it multiplicatively over time. So reduce to 0.95 and then reduce to 0.95 squared, so that it's basically working its way down from 1 to 0. And so what they got there was the reduced bias at the beginning. So they were more accurate at the beginning than tree backup. But as time progressed, it moved more and more. So basically this is a change over time from sampling to tree backup. Okay, so this is going eventually to 0.95 to the sum n, which is approximately 0. And this reduced the variance. So they ended up with, a good example was the root mean squared. This is for the, 19 state random walk. With the tree backup, with this descending sigma, they could basically end up with a 0 root mean squared error, okay? Which if you've already done the program assignment, we don't hit 0 with the algorithms that we're using. And if you use the sampling, you're always going to end up above 0 because you've got these samples that are happening where you're moving around the values. So the root mean squared error is never going to quite go down to 0. Questions?
Do we still never reach 0 if we use the weighted importance sampling?
So if we use the weighted importance sampling, well, in this case, when we're using n-step, sorry, you're talking about the importance sampling. So when using importance sampling, we're never going to quite reach 0 because we're always going to have this variance where we're bouncing around, right? If our behavior policy takes us to some particular not very likely action, that's going to get magnified in our importance sampling. And so therefore, we're going to move our value a fair amount. Okay, and it's either going to be up or down, but in any case, it's going to be around the true value as opposed to narrowing in on the true value, right? So we're going to be bouncing around as opposed to converging to our true value.
Okay, so even when we weight it so that we kind of like lower that volatility, the volatility will still kind of be there. Is that the essence of the idea?
So the weighted importance sampling, that's an interesting point, right? We did the weighted importance sampling. Let me just back up a second. I don't know how to do weights with n-step. So that is a question of how to do weighted importance sampling with the n-step, right? Here we're doing the non-weighted n-step per decision importance sampling. If we could figure out a way to do weighted, then maybe that would solve it, because you're right. When we did the weighted, that dampened it down and reduced the variance. Other questions?
So by that, you mean the ordinary importance sampling?
Ordinary importance sampling. Yeah, there were 3 kinds of importance sampling, right? If we look at this. So for the importance sampling, we had ordinary importance sampling. We had weighted importance sampling. And then we had per decision importance sampling. For our n-step, this is what we're using for n-step, right? So the ordinary importance sampling basically just said, look at your entire episode and then multiply the return of that episode by the product of the ratios of each separate action. The weighted importance sampling said go ahead and weight by summing by all of the weights that you have seen. And the per decision said, you know, if you're looking at the first reward, you don't really care about any later decisions. And so you just want to use the ratio, the first ratio. And then the second reward, we use the first and second ratios, and the nth reward, we'll use the first to the nth ratios. Did that answer your question, Rick?
Yeah, I was just forgetting what the weighted one was.
Yeah.
So is the reason why we're doing descending sigma, or why that was found to be the best, is because we're trying to gear towards exploration in the beginning?
No, it doesn't really have much to do with, so let's see. So the reason we want to end up with the tree backup is because we end up with this very low variance, right? So because we're doing this weighted mean, it damps out rewards that we're getting that have to do with unusual or improbable events. So when we end, right, if we've got some, let's just look at, this is time, and this is our value for some s, all right? We expect, and so if our true value is here, right? Ideally, you know, we're going to end up somewhere incorrect, you know, when we're going to move back and forth. But ideally, right, we have some variations, and those variations get less and less and less and less. And so the tree backup is going to give us this less and less variations. The advantage of descending, so if we just use the tree backup, we'll eventually get to both the true value and a low variance. So let me look at an example. So let's look at this one as, let's say this one's the tree backup. Okay, so we're gonna have a chart that looks like that. And let's now look at the importance sampling. We're going to more quickly get into the range of where we want to be, but we're going to have a high variance around it. So we're going to never get really close. And okay, so I only have one other color. Let's see, I can use black. The descending sigma tries to really have the best of both worlds. So it starts out like the green one. So it quickly gets in close here, but over time, it's going to reduce the variance. So like the tree backup, it eventually gets both a true value with a low variance, but it does it more quickly than the tree backup all the way.
Got it. Thank you.
Sure thing. Other questions? All right, so on Wednesday, we're going to start talking about planning, right? This idea of actually trying to estimate models and then using our models. Another way to think of it is really reusing our experience. So when we go ahead and interact with the environment, use those interactions not only to improve our state or action value estimates, but also to improve our model. And then we can use our model to also update our estimates. What else do we have going on? The programming assignment is due on, is it Friday, Thursday? Does anyone know?
I think Friday.
Friday? All right.
Hopefully.
Yeah, I think Friday is correct. I just don't have it right. I guess I can actually bring it up right in front of me fairly easily. Yeah, so that's Friday. We have, so the next programming assignment is going to come out until next week. Just verifying. Yeah, so we will have homework assigned this week, and we'll have a quiz. Well, so, oh yeah, that is the other thing we need to talk about is the quiz. So we do have a quiz. It's not in class. Instead, it's on Gradescope, and it's open through till I think it's 11 p.m. tonight. So go ahead and do that on Gradescope. I think it's 3 or 4 multiple choice questions. So it should be fairly straightforward. And I'm really not sure exactly how the grading works. I don't know whether the grading happens instantaneously for you or whether you all submit and then I go to look at them. Probably the latter. But the good news of that is we'll have it graded. I'll have that graded tomorrow. For a quick one. I will be available in this Zoom meeting until 3:30, and then I'll also be around tomorrow morning, the different Zoom meeting, which is on Piazza. I do have to, I'm not there from 9 to 10, so I have a doctor's appointment, a virtual doctor's appointment, so we'll see how that one goes. Other questions on anything? All right, thanks very much. The video will get posted sometime this afternoon. I don't have to worry about anyone in Russia editing it, so that'll be good. By the way, the Russian editor said he really enjoyed the last video because he doesn't know anything about reinforcement learning, and nothing other than that made sense, but he liked the financial one, so I thought that was sort of fun. All right then, thank you very much, and we'll see you on Wednesday, if not in office hours. Bye-bye.